NanoHub U, online instruction.
Hey everyone, welcome to lecture T13. In the last lecture, we just talked about the basic rationale for creating Camphor, which we said is somewhat similar to some of the other S-matrix methods, but uses an eigenmode to solve within each layer rather than using plane waves. And so now we'll talk about what kind of challenges that poses. So particularly like matching boundary conditions between different layers which have different eigenmodes may seem very tricky. Okay, but there is like an approach that can be used in general to deal with this sort of problem called Lorentz reciprocity. And so in Lorentz reciprocity, basically you would create some sort of arbitrary cylinder, which would look like this, and then you would evaluate Maxwell's equations across this boundary, presuming that the boundary is kind of in the middle right here of this cylinder, and make sure that they're satisfied so you can always be consistent with Maxwell's equations. And so, of course, this is just a way of rewriting Maxwell's equations here, but you can see that actually we've now split up E field into two different components, E field on the one side of the boundary in layer 1, and then on the other in layer 2. And so, of course, like within each layer, you just basically write down Faraday's law and Maxwell's, or sorry, I should say Ampere's law with Maxwell's correction. And then that gives you something like this, of course. And then instead of dropping the J, which we oftentimes do with Ampere's law for optics, we actually keep the J. And because that allows us to then combine some of these expressions together. So particularly we can take the cross product of E1 with H2, which is over here, and then we can substitute our expression for the curl of E2, and then basically we can write down that the curl of the difference between these two terms is equal to J dotted into E across these boundaries, like J1 dotted into E2 minus J2 dotted into E1. So the significance of that is then we can actually then put that into an integral, like over volume, and then we can use Gauss's theorem to convert this into surface integral. And of course, we can evaluate this, which is basically corresponds physically to power dissipation, like right in that volume of the Gaussian pillbox, as oftentimes it's called, the thing that I showed you earlier. And so the Lorentz reciprocity theorem just says that the rate of change of this surface integral has to be equal to the integral of these differences of J's dotted into E's. Okay, and so then that actually then usually allows us for Z invariant media to simplify it very quickly to something that just looks like E cross H across the boundary dotted into the normal direction would be equal to 0. And so that's like a very simple expression that allows us to ensure that like for whatever set of eigenmodes we have, as long as we combine them on each layer, then we can match them across the boundaries. And so just to go into a little more detail, you can see we can write E as basically a sum of these terms and would have to be equal to basically like the input wave plus the reflected waves and the transmitted waves, right? So of course, like these have to match like right on the boundary, all these E fields. And then you can define like the overlap between modes as essentially like using quantum mechanical type notation, like E as a bra and then H as a ket, and then integrated over this cross product across the surface, right? Because that matches up with Lorentz reciprocity condition. And then we can basically write down all of these terms here from this original equation as kets, and then cross those into bras, and then basically that allows us to simplify our terminology to calculate like both a transmission coefficient for each of the terms, and then also a reflection coefficient for each of the terms, right? So we've gone from essentially a very basic concept, which is the conservation of E fields and H fields across the boundary to a very specific set of transmission reflection coefficients, which would of course replace the standard Fresnel reflection in a more ordinary optical problem. And then, of course, once we have that, then it becomes fairly straightforward to use the standard S-matrix approach that we had already talked about previously. So I don't want to belabor that point, but I did want to mention that there's another reference from Lee, written in 1996, that kind of just shows the same formulation in a fairly compact representation. And then we can basically compose the S-matrix layer by layer in the fashion that we had discussed previously. So I won't go through that again in detail, but feel free to look back at that if you forgot. And then another thing that we can do that's really interesting with this sort of formulation or approach is that if we have periodic layered structures, like say just a simple repeated bilayer, a quarter wave stack, then we can actually write down a solution in the semi-infinite case would have to be an eigenproblem, where ABCD is essentially our repeated matrix, and then we would have some sort of like propagation coefficient through that repeated structure. And so now, of course, numerically, this could be a big problem for a T matrix because there's like these exponential terms, which I have here, especially if K had complex components. And so oftentimes we would use singular value decomposition to deal with this singularity. And so we would write basically this A matrix as a product of three different matrices, U and V, which are unitary, and then sigma, which represents the eigenvalues of the system, which is a diagonal term. And then that allows us to easily invert the A matrix in order to extract the forward and backward propagating modes, as well as like the corresponding wave vectors. And so in the next lecture, we'll go into more detail about how Camphor can be used practically.